So the next speaker will be Florian Pommerening, and he speaks about abstraction heuristics, post-partitioning, and network flows.
Thank you. Okay, so the questions we looked at, I'm sorry, I should have said this is joint work with Malte and Blai, both here. And we looked at network flows and how they relate to abstraction heuristics. And we are also trying to figure out why the state equation heuristic is faster than cost-partitioned abstractions, which are supposed to be more or less the same thing. But the state equation heuristic is much faster to compute than cost-partitioned abstractions. So if you don't know what any of these red words mean, don't worry about it. I'm going to explain this in a moment. So let's start with the first two, network flows and cost-partitioning. So a network flow intuitively is, you can think about this as taking a transition system and pouring a cup of water into the initial state, and then letting the water flow along the different transitions, and in the end the cup of water should pour out of the goal state. So formally we do this by assigning a number to each transition in a way that the total outgoing flow, so the summed up numbers for transitions out of the initial state is 1. The total flow into the goal state is 1. And in all other state, the flow balances. So there's exactly the same amount of incoming and outgoing flow. An abstraction, probably everybody knows, maps a transition system like this to a smaller transition system by identifying some states with each other. So in this case, we identify the middle two states. This turns some transition into self-loops. And a typical heuristic in these abstractions is just taking the shortest path in the abstraction. So this is what we call the abstraction heuristic. But using network flows, we can define the same heuristic based on flow. So instead of saying we want to compute the cost of a shortest path, we say we compute the cost of a cheapest flow. And this sounds like it's almost the same, and it's very close to each other. So what's the difference? The only difference is actually based on isolated cycles, like the one on the right there. So cycles like these that are not connected to any path can influence the flow because they actually can be part of a valid flow, but they cannot be part of a cheapest path. This usually doesn't matter, but if we are considering costs with negative actions with negative costs, we can get a cycle with negative cost here. So assume that the brown operator costs -1 and the red operator costs 0. Then we can repeat the cycle, or we can put a high number of flow on this cycle, and the cycle is balanced, so it's part of a valid flow, but it leads to an arbitrarily low cost. So the cost of the cheapest flow would be -infinity in this case. So we show in the paper that the flow heuristic in an abstraction is always less or equal to the abstraction heuristic, the cheapest path. But they are actually the same if we don't have any dead states in the abstraction. So the flow can be represented with an LP model, and this is a well-known thing. It's just minimizing the total cost of all transitions using the flow. I'm using count T here for the flow along a transition for a reason that will become clear soon. So it's minimizing the total cost subject to a constraint that is exactly the flow balance. So it has the incoming flow minus the outgoing flow, and that should equal 0 in case except for the goal and initial state where there's some special casing. So the reason why I wrote it this way is because this way we can connect this LP, so this the same LP as before, to the operator counting framework by just adding a linking constraint that looks like this, that says that the flow along the transition, so the number of times I'm using a transition summed up over all operators that label the transition, is the number of times I'm using this operator. And with this linking constraint, we can then replace the in the objective function this inner sum just by using the count for the operator. So this whole thing is then what we call an operator counting LP. It's minimizing the total cost subject to conditions that are necessary conditions for plans. And we can use this to combine heuristics for many different abstractions by just repeating these constraints here for any abstraction we want. And the theory on operator counting heuristic tells us that combining flow heuristics in this way is the same as computing their optimal general cost partitioning. So the general here means that we are considering negative costs, and this is why it's actually important to make the distinction between network flow heuristics and cheapest paths in abstractions. So in this paper we looked at this model, which we call the operator counting model for network flow, and try to find rules that simplify the model and make it smaller or cheaper, so cheaper to compute or stronger. So the first rule is really simple. I said dead states are hurting us. They can reduce the flow, and without dead states, the abstraction heuristic and the flow heuristic are the same. So the first rule is just to remove any dead states from the abstraction. The second rule applies to operators that only induce a single transition in the transition system. So here, for example, look at the blue operator. The blue operator only has one transition, so the linking constraint that links the operator count to the transition count looks like this. So usually this would say that the number of times we use the operator is the sum over all transitions it induces. But since it only induces one transition, the sum trivializes. This means we can use the operator count directly instead of the transition count and replace it in all flow balance constraints. This way we can remove the linking constraint and also the variable that talks about the transition. Okay, so the next rule is about operators that induce only self loops. So in this case, the green operator here induces a self loop on the goal state. And operators that induce self loops always cancel out in flow balance constraints. In the flow balance constraints, they count as outgoing and as incoming transitions, so they occur with a positive and negative sign and just cancel out. But they do occur in the linking constraint. But if the linking constraint only has these self loops, it doesn't actually tell us anything, because these variables never occur somewhere else. So we can just remove the linking constraint completely and get rid of the variables. And finally, the last rule talks about operators that induce regular transitions, like this one here, and self loops like this one here. So in this case, the red operator is one of those. So again, self loops cancel out in flow balance constraints. So we don't actually care about the value of this variable here, which means that we can remove this variable, but we have to adapt the flow balance constraint. So this here is an equation. So we call this the strong flow balance constraint. If we remove the variable for the self loop, we have to change it to what we call the weak balance constraint, a weak linking constraint, which has an inequality instead. Okay, so all of these rules reduce the size of the LP. Some of them can strengthen the model, but why are we doing this? What can we learn from this? And this is the last part of the talk, where we look at the state equation heuristic. In the state equation heuristic, this has different formulations that are derived from different models, but the original one is actually derived based on network flows in domain transition graphs, which are similar to projections, atomic projections. It was later extended to include merges of variables, where we consider two variables at the same time, and also partial merges, where we consider only some values of combining two variables, and also considering some mutex information. So with these, we previously thought that, or we previously published actually, that the state equation heuristic is the same as optimal cost partitioning of atomic abstractions. And this is not quite true. There's a small thing missing here. We said it's the same as atomic abstraction heuristics, but with the difference between network flows and abstraction heuristics, we now know that it's the cost partitioning of atomic flows. And the assumption that we are missing here is that if there are no dead states in these atomic abstractions, then the flows and the abstraction heuristics are actually the same, and then the result holds. And this is not a problem in practice, because a dead state in an atomic projection means that the variable has a value that is never useful, and such a value can just be removed, and usually is in preprocessing. So with the simplification rules I just mentioned, we can now completely explain what the state equation heuristic does, and we can not only do this for the basic heuristic, but also for all of its extensions. And we can understand them in the context of cost partitioning and cost partition abstractions. The other advantage of that we get is that we can use these rules to strengthen the heuristics. So as an example, I'm going to talk about variable merging. We previously thought about what this means, and we had a conjecture that variable merging would correspond to cost partitioned constrained abstractions. So considering the mutexes, remove some states from the abstractions, and it looks like it's related to constrained abstractions. And again, this is almost true, but not quite. It's the variable merging is actually slightly weaker. One thing is about the dead states that I mentioned before, but another thing that makes the state equation heuristic slightly weaker is about these linking constraints. The state equation heuristic always uses weak linking constraints, but with our rule we can show that some of these constraints can be strengthened to strong linking constraints. Okay. So I'm going to skip this a bit because I'm running out of time. This is just saying that the variable merging was previously only defined for two variables, and with these rules we now have a way of generalizing this to more variables and have a general way of doing partial merges. So to take home, in this paper we show that network flow heuristics are weaker than abstraction heuristics, but the difference is small and can be easily fixed by just removing dead states. And we introduce simplification rules that make the model for these flow heuristics smaller and stronger at the same time. And they also help us to understand, strengthen, and extend the state equation heuristic. So thank you.
Hello? So, in the end, at the beginning, if I understood correctly, you said that one of these two, the network flows, was more efficiently computable in practice than the cost partitioning on abstractions.
Mm-hmm.
So, this is because the constraints are slightly weaker, or?
No, it's the other way around. So actually, the state equation heuristic is the weaker one, but it has the stronger model, it has the smaller model. And the state equation heuristic is not as strong as it could be. We could strengthen it again, but in practice, this doesn't make a difference for the basic version, for the version that just looks at the atomic projections. So there it doesn't make a difference that it's actually weaker, but it still has a smaller model, and these simplification rules now help us to explain why it's faster. So we can look at the different rules and see which of the rules makes an impact, which makes the difference.
Have you already tried something of this in practice? Do you have experimental results?
Yes, so I don't have experimental results for the paper, but for my thesis I looked at some experimental results, and the interesting part is that the rules have different impacts depending on what size of projection we look at. So the basic state equation heuristic only looks at atomic projections, where something like dead states, removing dead states doesn't make a difference. And it's mostly about replacing these variables, these transition counting variables for operator counting variables. But then for larger projections, rules that remove the dead states have a larger impact.
Okay, there are no more questions. We thank Florian again.